Hi all, this is my second video for mth5106 integral equation. Okay, so in this video I'll talk on the integral equation and its classification, and some of the regularity condition, L2 function and L2 canal, right? So as we have discussed in the previous video, that this kind of equation is the most general linear integral equation. For the case of b is fixed, yeah, from a to b, where here b is fixed, then this is known as the most general type of Freedom integral equation. Okay, now from the general linear integral equation, yeah, if you consider g is 0, so we have here, if g is 0, so what we have with g is 0, so fx plus, yeah, from gx fx gx ux equal to fx plus lambda integrate a to b kxt ut dt. Yeah, this is the most general type of the Freedom integral equation. We call it Freedom because b is fixed, and where f, g and k are known function and u is our unknown function. Now if we set, g is 0, so what we have from there is fx plus lambda a to b xt ut dt. This is equal to 0. So this we call it as a Freedom integral equation. Freedom integral equation of the first kind. Yeah, Freedom integral equation of the first kind. Oh, sorry, back. Okay, and then again from there, if we set g is 1, if gx is 1, so what we have is ux is equal to fx plus lambda a to b kappa xt ut dt. So this is, we call it as a Freedom integral equation of the second kind, of the second kind. Okay, so the difference with first and the second kind is that for the second kind, we have the unknown function appears inside the integral as well as outside the integral, whereas for the first kind, the unknown function only appear in the integral sign. And if we set f is 0, okay, if you set f is 0, yeah, fx is 0, then so what we have from there, so we have ux is equal to, that is 0, so we have lambda integrate a to b kappa xt ut dt. So this is, we call it as a homogeneous Freedom integral equation. Yeah, homogeneous Freedom integral equation. Freedom integral equation of the second kind. Okay, so if you look at the notes here, that's our notes. Here should be 1.3.3 1.3, yeah, not 1.34. Mistyping there. Okay, and then the Freedom integral equation, which is not homogeneous, is known as non-homogeneous Freedom integral equation. Now we consider the Volterra integral equation. So the difference between Volterra and Freedom integral equation is that for the Volterra integral equation, the limit of integration here, the upper limit of the integration for the Volterra integral equation is a variable, whereas for the Freedom integral equation, the upper limit is a fixed number. Yeah, this is the most general Volterra integral equation. And so this is linear because u appear only once in the integral sign. Okay, and then again, if you follow the same procedure as in the Freedom integral equation, what we have, if we set g is 0, so we have from here g is 0. Okay, so we have fx plus lambda plus everything there is 0. So this we call it as a Volterra integral equation of the first kind. And if we set g equal to 1, so we have ux equal to fx plus lambda plus everything there. So here, this is the Volterra integral equation of the second kind. So we can see the difference here. Okay, this one, the unknown appear only in the integral sign, whereas for the second kind, the unknown appear in the integral sign as well as outside the integral sign. And for the second Volterra integral equation, second Volterra integral equation, if we set f equal to 0, then that give us the homogeneous Volterra integral equation of the second kind. Yeah, if the equation is not homogeneous, we call it as a non-homogeneous Volterra integral equation. Now we look at the next is the singular integral equation. We call it singular, singular integral equation. So when one or both limit of integration, when one or both limit of integration in an integral equation becomes infinite, or when the kernel of the integral equation becomes infinite at one or more point within the range of integration, then the integral equation is called singular integral equation. So this is for the example. If you can see here, both limits of integration are infinite. So this is the singular integral equation. And for this case here, you can see when x equal to t, so this the denominator is 0. So what happened? The whole terms there blown up. Okay, so that's why we call it as a singular integral equation for alpha between 0 and 1. Of course, for the case of alpha equal to 0, for the case alpha equal to 0, so this is give you 1, then we only have 0 to x ux ut dt. So that gives a Volterra integral equation, because this is the variable limit, upper limit. When alpha equal to 1, so that we call it as a Cauchy type singular integral. When alpha equal to 2, so I think I better write here. From this integral, so we have fx equal to 0 to x ut over x minus t squared alpha dt, for alpha 1. So for this case, we call it as a weak singular integral. If x is a fixed, upper limit is a fixed, then it's a Freedom integral, then in this case is variable, so this is Volterra type singular integral. Now if alpha equal to 1, so what we have here is, this is our equation reduced to 0 to x ut dt. So in this case our kernel of integral, this is just 1. Alright, so this becomes a linear Volterra integral equation with a kernel equal to 1. And if alpha alpha equal to 0 in this case, yeah, if alpha equal to 1, so we have fx is equal to 0 to x ut over x minus t dt. Yeah, we can see here the degree of singularity is 1, yeah, when x equal to t, when x equal to t, yeah, so we have singular point, there. So in this case the order of singularity is 1, so this is, we call it as a Cauchy type singular integral. Cauchy type singular integral. Yeah, when alpha equal to 2, so this, our equation becomes fx equal to 0 to x ut x minus t squared dt. So what's the difference between this and that? As you can see here, as when x minus t or x approaches t, the denominator will approaching 0 much faster than this one, and also much faster than that one. So in this case, this integral, we call it as a hypersingular integral. Hypersingular integral equation. Hypersingular integral equation. Okay, so that's a very specific. So we have a singular integral equation. Then I have defined you what is a weak singular integral equation. We have Cauchy type singular integral equation, and we have hypersingular integral equation. Next, we look at the regularity condition. What is the regularity condition? And square integrable function, an L2 function. So in the general form of integral equation, we have ux equal to fx plus lambda integrate a to b for the freedom. For the Volterra, you just replace b with x. So we have k xt ut dt. Yeah, freedom integral equation of the second kind. So we have the unknown ut, the known fx, and known kernel k. Yeah, each of these function satisfies the certain condition. Yeah, satisfy the certain condition. Now that condition is given here. We call it as a regularity. We call it as a regularity condition and square integrable function. So what are those? Yeah, the function ux, we call it as a square integrable function. A square integrable function if it is measurable, which is finite in the interval ab, and satisfy this square integrable. Yeah, square integrable means we integrate from a to b ux squared dt magnitude less than some finite number. So where the integral being taken in the sense of Lebesgue, so the above condition are called as the regularity condition. So the function u satisfying regularity condition is called as square integrable function, or simply L2 function. So when in the future, next, when I say L2 function, f L2 function, u L2 function, which means f or u must satisfy that condition. Okay, and same thing with the kernel. So we have a square integrable kernel, or L2 kernel. So the regularity condition on the kernel, k as a function of two variables, are broadly similar with some differences of detail. Okay, so let us consider a function k satisfying the following condition. So we have these three conditions. Okay, so kxt is a measurable function, which means finite of x and t in the rectangular region xab and tab, such that the double integral of that, okay, magnitude or absolute of kxt squared dx dt, that's finite, and kxt is a measurable function of t. Yeah, this one is measurable function of x and t. This one is measurable function of t for each value of x, such that if we integrate with respect to t, is finite. And as well as the third condition is that k is a measurable function of x. Yeah, of x. So for each value of t such that we integrate with respect to x, it is finite. Okay, so a function k satisfying the above three regularity condition, that's 3, 1, 2, 3, is called a square integrable kernel, or simply an L2 kernel. So while dealing with L2 kernel, we shall often have occasion to use Fubini's theorem and its extension by Tonelli and Hobson in order to justify changes in the order of integration in multiple integral. So I state here the following theorem without proof. Okay, first is the Fubini's theorem. If the double integral of f dx dt exists as a Lebesgue integral, then we have the following result. So those integral, if the integral exists, yeah, single integral of f(x)t, we integrate with respect to t, exists for almost all x, and is an integrable function of x. Yeah, which means if we integrate this, we end up with the function of x. Okay, and those function of x integrable, and the function of x is integrable, so such that the double integral f(x) dx dt, we can evaluate or integrate with respect to t first, then we can integrate with respect to x separately. Okay, and if the integral with respect to x exists for almost all t and is integrable function of t such that those double integral f dx dt fx. So look at the difference between these two. What we do here is that we change the order of integration. So this one is we integrate respect to t, then x, in this case respect to t, x, then t. Okay, and for the Tonelli and Hobson theorem, if f(xt) is measurable function of x and t, and any one of the three integrals, yeah, double integral of absolute of f respect to x and t, and that means we integrate respect to t and x, this one we integrate respect to x, then t. Yeah, if any of these three integral exists, then this integral f dx dt f dx exist and are equal to one another. So which means this equal to that, this equal to that. Yeah. So what we want to say here is that when f satisfy that condition, okay, so we can change the order of integration. You can change the order of integration without changing the value, so they are just the same. Okay, so there's two important theorem, Frobenius theorem and Tonelli and Hobson theorem. Then the last part in this video, yeah, if K is an L2 kernel, so we have defined what is L2 kernel, and G is L2 function, then it follows at once that this the integration of the kernel squared finite and from Schwarz inequality, so we have those integral is just less than that. Okay, so that the function is defined for all, that the function of x is defined for all x in the interval AB. I think we should have this thing here missing. Yeah, mistyping that. All right, so that's all for this video. So let me recap what I have defined in this lecture. So we basically, what we did is that we classify the Fredholm integral equation of the first kind, second kind homogeneous Fredholm integral equation, as well as for the Volterra integral equation. Yeah, we have Volterra integral equation of the first kind, second kind, and the homogeneous Volterra integral equation of the second kind, and also the singular integral equation. I have defined you what is a weak singular integral equation, Cauchy type singular integral equation, and hypersingular integral equation. Also, I have defined the regularity condition, square integrable function, as well as square integrable kernel. So with that, I thank you. We will meet again in the next video. Thank you.